Good morning, everyone. So the recording is now started, so we're ready to go. Just to reference the chat, yeah, this section 15.8, is not on next week's midterm. Next week's midterm covers up to section 15.8 on spherical coordinates. But before we dive into this section 15.9, I just want to do a little bit of interactive stuff right now. So a little bit of online polling, and this is in regards to the cylindrical shells and spherical coordinates. So let me just cut and paste a link to the chat. So if you go ahead and check the chat window and open that link, then it will take you to a page called Mathematize, and there'll be a question displayed there. The options for submission are not opened yet because I haven't opened the question yet, but it's an online polling question. So if you're familiar with clickers or online polling in Zoom for other classes, that's basically what this is, only it's math related in the sense that we can have math fonts in there and pictures and the like. So go ahead and click that link. And I've got a few questions, about 4 questions that are related to spherical coordinates and cylindrical coordinates. And so we'll just do a quick review. If you watch the videos, then you'll know these answers. If you haven't watched the videos yet, but you intend to, then this will be a little bit of foreshadowing to what you'll find in those videos, and perhaps a little bit of a quick bring you up to speed kind of discussion so that you can work on the homework assignment. All right, so I'm now releasing the question, so you can feel free to click on the corresponding response. In cylindrical coordinates, the volume element, so that dV, is given by what expression? Still waiting for about another 10 responses or so. All right, give me another 30 seconds or so to fire in your response. In cylindrical coordinates, the volume element is given by which expression? Oh, yeah, I will copy and paste the link. There you, oh, almost. So there you are. Anyone who's just joined the class, the link you can now see in the chat window. So you can click that link and answer the question. And just so you know, moving forward for the next few questions, even on this one as well, if you did select an answer, hit submit, and then you're thinking, oh, I need to change my answer, I don't see a way to undo my submission, you just refresh the page. Just refresh the page, and then you can submit a new answer. This is not tied, this is anonymous, right? You're anonymous here. So this is not tied to your SFU ID. You're not getting graded on this. This is purely for informal feedback. All right, it looks like we're getting all the responses in. So I'm going to stop the poll now and reveal the results. So the volume element for cylindrical coordinates is essentially the volume element coming from polar coordinate area element times the change in the z direction. So it's basically r dr d theta with that dz for the change in z thrown in. So I've written it here as r dz dr d theta. So it's an extension of polar coordinates with one more variable, the z variable thrown into the mix. All right. So whenever we're doing a triple integral and we switch to cylindrical coordinates, essentially polar coordinates in the plane with cylindrical, or polar coordinates in the plane with the z coordinate going in the upward direction or the perpendicular direction, then the volume element in our triple integral becomes r dz dr d theta. All right, let's have a look at the next one. In spherical coordinates, rho, theta, phi, what is the volume element given by? In spherical coordinates. So while you're answering that, I will just write down our results here. In spherical coordinates, what is our volume element dV given by? Another 30 seconds to fire in your response. Okay, here we go. Closing the poll, revealing the answer. And I'll bring my window over as well. So the correct answer is rho squared sine phi d rho d theta d phi. So that's in spherical coordinates. We have this adjustment factor, like in polar or cylindrical coordinates, we had that adjustment factor of r. That's basically how a volume is changing by a scaling factor when we switch from one coordinate system to another. In spherical coordinates, this is our scaling factor, rho squared sine phi d rho d phi d theta. So one thing you can notice here as well is you'll get your result back. It'll either say correct or incorrect. You can always click on that button above View Classroom Results. And if you click on that button above, you'll see what the response is from the group as a whole. Look at how the distribution was done amongst the various answers, just out of your own curiosity. When I do clickers, I always like to show the group response, and so you can have that option as well. All right, next question. So there's the question. You may need to, depending on the size of your browser window, scroll up or down to make sure you've got the whole thing. But it's asking true or false. There's a solid that's drawn there. Is it a spherical box? That is, can you describe that solid by a system of inequalities of the form rho is between two constants, theta is between two constants, and phi is between two constants? So the question is now open for you to put your submission in.
I'm sorry, Jamie, Was a little
Yep.
bit late this morning. I
Oh,
don't know where we're going here.
all right. I will cut and paste the link into the chat window. There you go. Sorry, it's the unfortunate thing about these Zoom chat windows is when you come in after I put something in the chat, you don't get to see it. So there's a link in the chat window now. And so you just click the link and there'll be a poll question open.
Thank
And
you.
you can just go ahead and answer the question. For all those coming in, of course, when you click the link, you're right onto the question. So you can probably infer that this is anonymous. This is not for credit. This is not for grades. This is purely just for a summary of cylindrical and spherical coordinates, or perhaps a little bit of, if you haven't watched the videos yet, a little bit of foreshadowing as to how they're being used this week. All right, so is this region there, that's sketched, is that a spherical box? Where our goals with things like spherical boxes are regions that are complicated when you deal with them in rectangular coordinates, but when you switch to polar coordinates, their limits of integration are all constant. And so that's a question about, is the region you're integrating over a box in that coordinate system? So that's what this question is asking. Can we look at this region and say, yes, that's a box in spherical coordinates. Rho is trapped between two values. Theta is trapped between two values. And phi is trapped between two values. All right, another 5 seconds or so to get your response in. 4, 3, 2, 1. And the results are out to you. And we got about 82% of the class said true, that it is a spherical box. And indeed it is. This is a spherical box. And so I'll scroll up. There's our region up here. You're also getting a bit of a prelude, the image below, as to what the next question is, at least what the region is. So this is our region that we're interested in. We want to know if it's a spherical box. It's really asking, can we describe all points in this region by inequalities on the variables, which are bounded by constants? And the idea is, yes, we can. If this is our x-axis, then what we're doing is we are letting theta sweep out all of those values. So theta is allowed to sweep out all values between 0 and 2 pi. What is phi sweeping out? Phi is sweeping out all values from being like a value on this cone down to a value on this plane. So that's our phi value. Maybe I'll show write theta in here. So phi is sweeping out all those values, which is whatever that first value is. Phi equals, I don't know, whatever I called it in the question. Phi equals, I said m. So it's some constant m. And in this case, it's all the way down to pi by 2. And rho looks like it's sweeping out. It's got all the distance from the origin. It looks like it's sweeping out 0 all the way up to, and I could read a number off of the axis there, all the way out to 1. So regardless of what those actual values are, there are constants here that these variables are trapped between, and so it is a spherical box. So this is a spherical box. You can think of it as this is in some sense the complement of that cone, at least in the upper hemisphere. We had a cone in our examples that we were doing in the video lectures with a little ice cream sitting on top in some sense. Like that. This is what we looked at in the lecture. That's also a spherical box. So this ice cream cone is a spherical box. Phi goes from 0 to m in that case, and theta is 0 to 2 pi, and rho goes from 0 to whatever it is, 1 in that case. So that's a spherical box, and then the complement of it, also a spherical box. So these are various things that in the spherical coordinate system, much easier to integrate over than they are in the rectangular coordinate, because these have all constant limits of integration for the three variables. Let's look at the last question. So how about this region here? I can actually just show it in this region here. It's on the slide, but you can also look at it in the browser. I didn't want to have things on the share window at the same time as you looking at your browser. So looking in your browser window is that blue shaped region a cylindrical box? Is Z trapped between two constants? Is R trapped between two constants? And is theta trapped between two constants? I've just posted the link in the chat if anyone has just joined us and is wondering what we're doing, because people seem to be working on something that's not on the screen. It's because it's in their own browser window. So in the chat window, there's a link. If you click on that link, you'll see a question appearing. So another 20 seconds or so to get the response in. Is this region a cylindrical box? No. Close the poll now in 3, 2, 1. And there we go. Poll is closed. You can click the responses tab. We got about 75% of the class said true, that this is a cylindrical box, and yes, it is. Z is trapped between two values. You know, in some of these three-dimensional regions, I haven't given you equations or anything, so I'm just merely going from the picture. It might be hard to see unless you could rotate it around. The idea is that it looks like we got a flat top in terms of the Z directions and a flat bottom. So it looks like these are constant Z values. So Z is equal to some whatever value. So I'll say N, and this is Z is equal to some other value M. What are our R values and our theta values? Well, in some sense, our theta value is running over all of these values here. So theta gets to run over all of those values. And our R value is looking like it's trapped between two different values as well. R is equal to, I'll try to get the same variables I used. R is equal to A versus R can go up to B. And so this is a spherical, or sorry, a cylindrical box. It's less than N, bigger than M, and theta goes from some value C to some value not B, some value D. So there's a question in the chat. In all the examples using cylindrical coordinates, we let Z vary vertically and put X and Y in polar form. Exactly. X and Y, so in cylindrical coordinates, it's a little bit more restricted than just what we did with polar coordinates in the previous chapter, or the previous section. In section 15.6, we changed to polar form when it was convenient to do so in whatever coordinate plane that we wanted. In this section on cylindrical coordinates, it's always switching the XY coordinates to polar form. So we're very restricted in that sense. So in some sense, when we talk about doing a switch to polar coordinates in a plane and leaving one of the other variables as is, that is a more general version of cylindrical coordinates. Cylindrical coordinates is always taking the z value to be constant. It's constant, always taking the z value to be the same variable, z, and switching x and y to polar. Yeah, good question, Graham. So yeah, the cylindrical coordinates in that sense is just a restriction or a specification of our polar form. Spherical in this case is switching all three coordinates. So in spherical, we no longer have x, y, or z remaining the same. We've switched all three of them to these new variables. And these new variables are going to represent so with the x, y, and z coordinate system, that was, we had three coordinate axes that were mutually perpendicular, x, y, and z. And then we looked at the distance. So where is a point in space? It's defined by its distances from these coordinate planes, the xy plane, the xz plane, and the yz plane. Those are all our three components of our coordinates of our point. But in the spherical coordinate system, we now switch all these to different coordinates. The point in space for spherical coordinates is how far is it from the origin. That's our rho value. And then we say, okay, once I project that point down here into the plane, what was the angle that was swept out? That's our theta value. So our theta value is roughly the same as it is in cylindrical coordinates. It's just this sweeping angle. And then the other question is, how far, when I look at this line segment that connects the point to the origin, what's the angle that's made with the vertical axes? That's our phi value. I sort of refer to this as the dropping angle. How far do I have to drop from the vertical to get to that point? And those are our three variables now in the spherical coordinate system. And I'll review what those are in terms of the xy values in this lecture, because we're actually going to look at a particular example of this. All right, so we're done with the 4 questions, the polling, so you can get rid of that browser window if you want to. And we're now going to get into today's topic. So what today's topic is it's just general change of coordinates. So in general, we've got an integral, double integral, triple integral that we want to work with. And the region we're integrating over is challenging. So if the region is challenging in the coordinate system we're working in, we will try to change to a new coordinate system, and that's referred to as a change of variables. So the change of variables into polar coordinates, that's one example. Into cylindrical coordinates, that's another example. Into spherical coordinates, that's another example. Now we're just going to look at general changes of variables. This is motivated by things we did in Calculus 2. So for example, in Calculus 2, we had integrals like this, the integral from 0 to 1 of x root 1 plus x squared dx. What did we do in order to evaluate this? We did what was called a substitution. We said something like, oh, well, we'll take u is equal to 1 plus x squared. Du is equal to 2x dx. We'll look at the limits as well. So when we change the variable, we can change the limits. Our limits of integration are upper one is x equals 1, lower is x equals 0. Those become, I'll give myself a little bit more room here. I might be hiding myself behind my picture. When x is equal to, oh, wrong one. When x is equal to 1, we've got u is equal to 2. And when x is equal to 0, u is equal to 1. So that's how our limits of integration have changed. And so then we've got that this integral can be rewritten as the integral from 0 to 1 now becomes the integral from 1 to 2. The 1 plus x squared becomes a root u. the x dx becomes a 1/2 du. And so that was the idea with this thing called substitution. We try to make a change of variables. See now where this is coming in, tying in with this current lecture. Change the variables. U is equal to 1 plus x squared. And we go and re-express this integral in terms of the new variable u and its limits of integration. So our original integral, oops, I don't need to draw, a one-dimensional thing. Our original integral was over an x-axis from 0 to 1. So it was over that portion of like the x-axis there. And what we did was we changed to a new variable, u, and we're now integrating over the interval for the u variable over 1, 2, while at the same time our integrand changed. So I'm going to write it one more way. So this substitution in general. So we can write substitution as the integral of f of x dx is equal to the integral of, actually I'll write it f of u du. Sorry, I'll switch these to u's. F of u du is equal to the integral of f of g of x g prime of x dx. So that's our general formula we've been using for a substitution. We typically go from the right side and rewrite it in terms of what's on the left. We usually take an integral that has a complicated integrand, f of something g of x, where that g of x's derivative is also in the integrand. Above, the g of x would have been this. So here, I'll put it in a different color because it's sort of referring to what's down below. Our g of x is our 1 plus x squared in this case. And our f of x in this case is just the root x. If we're going to make the comparison with what's below. So what's below is we've got an integral of the square root of 1 plus x squared times the derivative of the 1 plus x squared, or the g of x, up to a scalar. So there's a 1/2 that sort of needs to be accounted for, and that's what we've done in the substitution. So that's what a substitution is. So it says we can always take our integral, and I'm going to say this in the opposite way because this is actually helpful for us. We can take an integral like this, f of u du, and we can always rewrite it as an integral in this form, and vice versa. So we can always transition back and forth between rewriting the integrands in this way. And we typically, as I said, go from right to left, complicated integrand to simplify it. Now we're going to do the same thing here. The key question, though, is how does the integrand change? We're going to replace our x with some function of u and v. We're going to replace our y with some function of u and v. And then we got to replace our volume or area element, in this case area element, because I only said 2 variables, with some change. What's the change in our area element? If it was a polar change of coordinates, the change in our area element has this extra factor of an r. If we're looking at 3 dimensions, cylindrical coordinates, we had this factor of an r that caused a change in our volume element. Or in spherical coordinates, a rho squared sine phi that has a change in our volume element. In other words, this thing here, which was how our differential changed with our substitution, that g prime of x, we have to figure out how that thing actually gets updated with a change of variables. So that's our goal, is to extend the idea of substitution to multiple integrals. So let's have a quick refresher. So this is a reminder. It's basically a reminder only if you've watched the spherical coordinates video yet. If you haven't yet, then this will give you a foreshadowing of what that is about and what we're doing on this week's assignment. So where E is enclosed by the sphere, so we're integrating over E, where E is the region enclosed by the sphere in the first octant. So we've got our portion of our sphere in the first octant. So I'll just try to draw what is going to look like a sphere here. Hopefully it looks like a sphere, or at least an eighth of a sphere. So that's the region we're interested in. The idea is that in spherical coordinates, this is a box. And so we can write it with certain inequalities on the variables. So what is our change of variables for spherical coordinates? How do the x, y, and z change? Well, this is a rho sine phi cos theta, rho sine phi sine theta, and a rho cos phi. So that was how our spherical coordinates are defined for sphere. That's how our spherical coordinates are defined in this coordinate system. And what else do we have? We have that theta. So now I want to describe this box. Theta, I'll go in the order that we typically list these. Rho, theta, and phi. So rho this is a sphere of radius 3. So rho goes from 0 out to 3. We're in the first octant, so theta goes from 0 to pi by 2. And phi goes from 0 down to pi by 2. So this is our spherical box. And that means what we end up doing is when we want to integrate over this box of this function, x squared plus y squared plus z squared dv, we have changed our limits of integration to the new variables. So maybe I'll go rho inside, 0 to pi by 2, 0 to pi by 2. And then we update our function, our integrand, so that it's rewritten in terms of the new variable. In this case, it would be e to the rho, because x squared plus y squared plus z squared square root is just the distance that a point is to the origin, and that's the rho value. And then we have a rho squared sine phi d rho d theta, or d phi d theta. It doesn't matter which order I write these ones in because they have the same limits of integration. So I'll go d phi d theta. And so that was what we've done with our spherical change of coordinates. We change the limits of integration to match our new coordinates, and then we update our integrand for those new coordinates. And we got this update to our volume element. There was our old volume element, and there was our update to it. And so we got this funny rho squared sine phi coming up. And this comes from our change of variables. It is essentially like playing that analogous role of that g prime that's sitting up here in our substitution case. We changed the u's to x's, and we had this extra g prime that appeared in front of the dx. That's what this rho squared sine phi is playing the role of. And so we have to always put that in there because that's a part of the change of variables, but we're going to see today where that could potentially come from, or where it comes from in general. Okay, so that's one of the things we want to answer. So now let's have a look at another integral. This one's a double integral. We want to evaluate the integral over this region R, which is a trapezoidal region, with the following vertices. So this is x, y. I've written it so that we're going to be working below the x-axis just because we see that there are some negative y values in our points that are listed here. So we've got a 1, 0. So that's 0.10. We've got a 2, 0, we've got a 0, -1 point, and we've got a 0, -2 point. So those are the 4 points, are the vertices of our trapezoidal region. So we can connect those points up. And there's the region that we're interested in integrating over. That's the region we want to integrate over. That's our region R in this case. Now there's going to be a couple of challenges here. One of them is the integrand is an e to the x plus y over x minus y. That looks to be a bit of a problem. Might be tough to find the antiderivative. So that's one thing that we need to be aware of, just looking at this. That might be tough to find the antiderivative of that thing, regardless of whether we do an x or a y first. The other thing is this region is neither x simple nor y simple. There's not just one curve that's sitting as the upper curve and one curve that's as the lower curve, or there's not just one curve as the left curve and one curve as the right curve. So is there, maybe I'll put this is the big question, is there another coordinate system where this is x simple? Well, I shouldn't say x simple, where this is simpler, maybe I'll just say. I don't want to say x simple because in our new coordinate system, x won't be one of the variables. So where this is simpler. So could I find another coordinate system which turns it into a box in that new coordinate system, or at least makes one of the variables trapped between two constants? Yeah, good observation, Mitchell. You're going to take one of your coordinates to be u equals x plus y. Excellent observation. And so that's the nice thing about that x plus y is, well, let's see why we would want to do that. This line that goes from 0, -2 up to 2, 0, that is an x. Well, what is it? We can write down the equation of this line. It's essentially, maybe I would write it down this way. It's going to be, it's going to be linear because it's a line, and we want it to have the property that what happens? We want it to have the property that it passes through these 2 points, 0, -2, and 2, 0. So maybe if I took it to be something like x minus y is equal to, let's see, what would that give me? That would give me a -2. If I plugged in the values here. Oh no, that would give me a 2. X is 0, y is -2, so that would give me a value of 2. And then if I look at that upper point, 2, 0, 2 minus 0, also 2. So that equation for that line is x minus 2 equals, or x minus y equals 2. And that's just a quick way to do it. I got 2 points on it, so I'm just going to write them down. You can find this equation of the line however you like to find equations of lines. And then we've got an x minus y equals 1 as that equation of the line. And so that starts to suggest that maybe x minus y, because x minus y is 2 and x minus y is 1, maybe that's what we're going to want to take one of our variables to be, an x minus y. And the other way is to sort of follow what Mitchell perhaps looked at, and that was in the integrand, we've got an x plus y over an x minus y. So maybe to simplify that, I'll take the x plus y, the thing up top, and make it one of the variables. So however we decide to do this, we're looking at trying to simplify the integrand and the region. So let's have a look at the next problem. So these next few problems are all related, and it's doing a little bit more exploration of this one. So consider the transformation defined by taking uv values and creating xy values from them in the following way. X is 1/2 u plus v, y is 1/2 u minus v. Let's sketch this region, this rectangular region, v between 1 and 2, And, oh, sorry, it's not rectangular. It's V is between 1 and 2, and U is between negative V and V. So not a rectangular region, but a region we can sketch nonetheless. So we'll look at the UV plane, and we're going to sketch this region S. V is trapped between 1 and 2. No, that's not 1, that's 2. And here is 1. U is trapped between negative V and V. So there's our U equals V line. And then we've got the U equals negative V line over here. Probably should have given myself a bit more room, because now that line doesn't look exactly like a U minus V line. So let's try to make it come out a little bit further. There we go. That looks a little bit better. It looks a little bit more symmetric. And we're interested in the region that's between these two and between this value for V. So we've got our U equals V, our U equals negative V, and our V equals 1 up to V equals 2. So this is our region. That's S. So very nice, in this case, horizontally simple region, or a U simple in this case. It's a U simple region. And what I'd like to do is I'd like to see under this transformation, which I'll call T of UV, which is going to return, for the X value, it'll return U plus V, and for the Y, 1/2 of U plus V, and for the Y value, 1/2 of U minus V. So for this transformation, what does this region become? So I already know in advance how to draw my coordinates, so I'll draw them like this. But it won't be clear just by looking at it at first glance. We'll probably have to draw the full coordinate system and figure out where things lie, but I'm going to draw it because I actually know things are going to land in the 4th quadrant. So how do we figure out where this region gets mapped to? Well, the idea is this is linear. Right? This is a linear transformation. And now at this point in the course, if you're taking linear algebra concurrently with it, you will have studied linear transformations by now. So this is a linear transformation. You can write it down as a matrix transformation. And it takes, what linear transformations do is they take lines to lines. So what I just need to do is figure out where these 4 points go, because the lines connecting them will just remain as lines connecting the points as to where they go. So let's start with these various points. So this point here, that's 2, 2. Where does it go to? So we plug it into our expression for T, 2, 2, that goes in for U and V. The first coordinate becomes 2 plus 2 over 2, or 4 divided by 2, which is 2. So that has an X value of 2. And the Y value is U minus V 1/2, so its Y value is 0. So that's where that first point went to. This is T of 2, 2. What's our next point? Maybe I'll do this point here. This point here is going to be 1, 1. Where does it go to? Well, it gets mapped to 1 plus 1 over 2, or 1. And the Y value, or sorry, the Y value is 1/2 U minus V, or 1/2 1 minus 1, which is 0. So it gets mapped to this point, which is 1, 0. So that's T of 1, 1. And the line that goes between them, draw a little arrow indicating on our diagram on the left, the blue arrowhead, the line that goes between them maps to the line that goes between these two, because it's a linear transformation. Lines go to lines. And now what next do we have? Maybe I'll take the next point. Let's take this one here, which is point -1, 1. And in that case, taking u to be -1, v to be 1, the x value under our transformation becomes 0, and our y value becomes -1 minus 1 is -2. A half of that is -1. So this becomes 0, -1. That's our t of -1, 1. And our last point, which I'll put here as our purple point, that is -2, 2. That gets mapped down here. Extend this a little bit further to 0, -2. So that's t of -2, 2. And so our lines that are connecting all of these points get mapped to lines that are connecting these points. So our region gets mapped to this. So T takes this region, S, and maps it over to this trapezoidal region in the XY plane. And so that means T inverse would do the opposite. T inverse would map it in the other direction. And what is T inverse? We can just solve the corresponding equations for, so x is some expression in u and v, y is some expression in u and v. We can go ahead and we can reverse those expressions and have a way to go from xy back to uv, and that would be x plus y and x minus y. So that's what that map in the opposite direction would do. So now this gives us a way to say if we're ever dealing with that thing on the right, that trapezoidal region, which we were going to have to in dealing with this integral at the top of the page, instead we can change to these UV coordinates, and then our region becomes the region S on the left, which is much simpler to deal with. So we can switch coordinates and deal with a simplified region of integration. The only problem is we then need to figure out, once I've simplified the region of integration, actually my limits of integration, I still need to know, how does the area change? I can't just go ahead and put new variables in without figuring out how my area element, how does dA change? So how does this change of variables affect a double integral? i.e., how does dA change? And I'll give you a bit of a hint, actually more than a hint, we'll actually go through it and see. So we've got our transformation, which I'll write down as a matrix. So this is our transformation, which takes UV values and produces XY values. So that's the moving from left to right in our picture up above. And I'd like to know if I had a little square on the left, a little square in my region S on the left, and I take its transformation, what kind of shape does it become on the right? And what's its area? So I'm going to take, for here, a square of area 1 on the left. Let's just see what happens. So if I take an area 1 square in the UV plane, sorry, area, I said plane and then I wrote down plane, area equals 1, a little square of area 1, and I look at what happens when I map it under T. What does it become? Well, the thing to keep in mind is now we're borrowing on our linear algebra skills. How does this rectangle get mapped? Well, I just need to know, what does it do to these two vectors? What does it do to E1? What does it do to E2? There's two standard basis vectors. When I take their image under T, T of E1, which is T of 1, 0, that gets mapped to 1/2, 1/2. And T of E2, which is T of 0, 1, gets mapped to the second column, 1/2, -1/2. So these get mapped to that one and that one. So that's T of E1 and that's T of E2. And they form this little parallelogram. And what is the area of that parallelogram? Well, I have the vectors here. And so we can see that we can find the area of this thing just because I have the two vectors that make up the sides. And the area is a half. I've got a half and a half for one side vector and then a half and negative half for another side. So this is a object whose area is a half. And so the answer to our question is, how does the area change? The area of a region of size 1 has now gone to an area of size a half. So this is shrunk areas. This transformation is shrinking areas. How can I detect this? What is it related to? Where did this half come from? Well, here's where the half came from. If we take the determinant of the transformation, then the determinant is negative a quarter minus a quarter or negative a half. If I take absolute values of that determinant, then I get a half. And that is how we can detect how areas are changing under transformations. That's what the determinant is really telling us. It's telling us how these scaling factors happen. In this case, it's telling us the area scaling factor. What is the negative telling us? It actually tells us something interesting as well. The negative coming up in the determinant tells us that there's been some sort of reflection in a change of orientation. Notice that if I go counterclockwise, E1 to E2 is the shortest angle. There's the smallest angle. That means going from E1 to E2 on my left-hand picture, that's the smaller angle. But then in my picture on the right, they've been reversely oriented. The E2 is now, or the image of E2 is now on the other side of E1. So there's this change in orientation, that's the negative sign. But the orientation change is not going to affect our volume or our area or whatever it is we're looking at, in this case, area. Area is just the magnitude of the determinant and how that got changed. And this is a half. So area change is the thing that we're going to need to know in order to find dA. This was a linear transformation. It was related to its determinant. For a non-linear transformation, it's still related to the determinant, but we have to split it up into little patches and use calculus on the little patches to roughly approximate them by things that are flat. So that's all the ingredients we need. Next day, we will go through and we will present the full change of variables and then do some examples. So that's it for today.